This is lesson 6-3, 6-4 in the Forrester textbook, and the topic of today's lesson is going to be properties of logs, and this is a log. I'd like you to take notes on what you see today, and what you're going to see is a total of 6 different properties of logarithms which we are going to use in order to make derivative and integral calculations easier for us. And right now we're going to get the first 2 properties, and they come from the fact that logarithms and exponents are inverses, meaning they undo each other. So for instance, suppose we've got some value. I'm going to call this value smiley face. And we take e to the smiley face power. So now we've done something to it. And then we do the inverse operation of e to it. We take the natural log. Well, if you take the natural log of e of smiley face, the e and the natural log undo each other and we end up with smiley face. Likewise, here's number 2. Suppose we start with smiley face. And the first thing that we do to smiley face is we take the natural log of him. We then take that value to the e power. Again, the e and the natural log are going to undo each other and we end up with smiley face. So let's look at how that fact is going to allow us to simplify some calculations. Example. Take the integral of the natural log of e to the x squared dx. Now this right here is an absolute mess, and if you try to do a u substitution or anything else, it won't work. But you might know that we have this x squared here, and we're doing the natural log of e to it. Therefore, we can rewrite this expression simply as x squared dx. And that is a piece of cake to integrate. We end up with 1/3 x cubed plus c. How about another quick example? Let's take a derivative this time. The derivative with respect to t of 5e to the natural log of t. And so you could do this the long way, and if you did it, you'd still get the right answer, but it would be messy. The quick way is to note that we can use our inverse properties to simplify that statement. So this is equivalent to the derivative with respect to t of 5 times that whole thing is just equal to t. And now we can take the derivative. The derivative of 5t is equal to 5. What I want you to notice was true of both the first example and the second example is that before we attempted to do the calculus, an integral in the first case and a derivative in the second, we first simplified the expression. Simplify the expression. Number 3. Something called the product rule. You've seen the product rule before. Part of today's lesson is to get you to a point where you can see where it is derived from. So I'm going to start with this. We've got the natural log of something, we'll call A, plus we've got the natural log of something else, which we're going to call B. And I'm going to take that and I'm going to rewrite it using logs and exponents. So imagine that that a plus b, natural logs of both, is up in the exponent, taken to the e power. Now when we took that to the e power, we changed its value. And so we've got to cancel that out by now taking the natural log, right? Remember our property up here, the natural log of E of smiley face is just smiley face. Well, that's what we're doing here, except for in place of smiley face, we have the natural log of A plus the natural log of B. All right, now check out what happens over here on the right side of the equation. Since we are adding in the exponent, we are allowed to rewrite that as e to the natural log of A times e to the natural log of B. That is an application of exponent properties. Oh, and look at this. We know what that and that are equal to. This is the natural log of, that's just an A, times this is just B. Again, using those inverse properties. So the moral of the story is that if you're taking the sum of two natural logs, it's equal to the natural log of their product, hence the product rule. So let's look at an example of a problem that we can solve using this product rule. So we want the derivative with respect to x of the natural log of x to the fifth times the cosine of x. And you could do this problem already, but keep in mind that we would have to use a chain rule, so it would be 1 over the inner function times the derivative of the inner function, which is a product, and that's going to get messy. So what I'm going to suggest is that instead you could note that we have a product inside a log. And if we have a product inside a log, we may rewrite this expression as the natural log of the first term, the x to the fifth is acting like A, plus the natural log of the second term, the cosine of x is acting like B. Well, now we've got two separate expressions to take the derivative of. The first one, we would say, all right, outer function is natural log, inner function is x to the fifth, so we get 1 over the inner function multiplied by the derivative of the inner function, plus second expression. Outer function is natural log, inner function is cosine, so we get 1 over the inner function multiplied by the derivative of the inner function. And look how nicely this cleans up now. This expression right here simplifies to 5 divided by x, and this expression right here simplifies to minus sine over cosine gives us the tangent of x. And so by applying the product rule and expanding before we took the derivative, we were able to get our answer more simply. Let's look at another one. Property number 4 is the power rule. You've seen the power rule before, but again, my goal is for you to be able to derive it. So let's start with this. Suppose we've got some value n multiplied by the natural log of x. And just like we did with the product rule, let's rewrite this in the exponent. In fact, pause the video for just a moment and see if you can rewrite this expression in an exponent so that this box and this are equivalent. Okay, and so now I'm going to give you the result. The natural log of e to the n times natural log of x. And so if we look at this expression right here, concentrate on the e part, this can be reorganized. I'm going to write it as natural log of e to the natural log of x times n. All I did was I replaced these two terms, or I switched them using the commutative property. And once we do that, we've got something useful going on right here. Using inverse properties, e to the natural log of x is just x. So we have natural log of x to the n power. And so the power rule says that if you have a coefficient on a natural log, like we do right here, it's simply equal to the natural log of the function inside to the coefficient power. So the n goes here. Let's look at an example where that might be helpful to us. Take the derivative of the natural log of 9x to the 8th power. Now again, this one's not that hard to do straightforwardly, but we might go ahead and notice that we've got an exponent and we've got multiplication. So before we take the derivative, we could break this thing apart. Let's do that. Natural log of 9, since this is a product, when we expand we add, times the natural log of x to the 8th power. But that's not all. We could break this down further into the natural log of 9 plus, let's take that exponent and pull it in front, 8 times the natural log of x. And now we evaluate. And what you'll notice is that when we evaluate this, the derivative of natural log of 9 is just 0, because this right here is a constant. Plus, the 8 is along for the ride, times the natural log of x has a derivative of 1 over x. Therefore, our answer is 8 over x. That's the end of video 1. Stop this one and go to video 2.